All right, get ready for this one. We're going deep on vectors. You might think they're just something you see in a physics textbook,
Yeah.
but trust me, they're kind of the secret language behind so much more, like
Yeah.
how planes navigate, how video game characters move,
Mm.
even how bridges are built to withstand all those forces pushing and pulling on them. We've got a really cool interactive resource designed for secondary students
Oh, cool.
that's going to help us break down this key concept called vector components.
Yeah, it's true. Vectors often get overlooked,
Yeah.
but they really are everywhere
Mm-hmm.
once you start to see them. And these components, as you call them,
Yeah.
they're really like unlocking a secret code
Right.
to understand how things move and interact in the world.
Okay, so before we crack the code, let's make sure we're all on the same page.
Right.
Remind me, what exactly is a vector?
So a vector is a quantity that has both magnitude and direction.
Okay.
Think of it like a set of instructions. It tells you not just how much, but also which way.
So it's not enough to just know how fast a car is going. You also need to know if it's heading north, south, east, or west.
Exactly. That's what makes it a vector, that combination of speed and direction.
Okay.
And the resource gives some other great examples, things like displacement, velocity, acceleration, and force.
Yeah.
They all have a size and a direction
Right.
working together.
Okay, so like with force, it's not just about how strong the push or pull is,
Right.
but also the direction it's acting in. So are all quantities with magnitude and direction vectors?
That's a good question. And it's actually a bit of a misconception.
Okay.
While it's true that vectors must have both magnitude and direction,
Mm-hmm.
not everything with those two qualities qualifies as a vector.
Oh,
They also need to follow specific rules of addition.
interesting.
Okay, example, angular displacement and electric current have magnitude and direction, but they don't quite fit those rules.
Okay.
And so they're not considered vectors.
Interesting. So it's like there's a secret club of quantities that get to be called vectors. Right.
And they have their own special set of rules.
Exactly.
Okay. So we've got a handle on vectors themselves.
Mm-hmm.
But what about these vector components?
Yeah.
The resource kind of makes them sound like a shortcut.
Yeah. That's a great way to think about it. The main idea is that we can take any vector that's at an angle
Okay.
and break it down into two simpler parts, one horizontal and one vertical. These are the vector's components.
So if we had a vector pointing northwest,
Mm-hmm.
it would have a bit going north and a bit going west, like we're separating out the northness and westness.
You got it. And what's really cool is that the resource has a visual that shows you exactly that.
Oh, nice.
You can see how that diagonal vector is split
Okay.
into its horizontal and vertical parts.
Okay, I'm starting to see the shortcut aspect. But why is that so useful? Why would we want to break a vector down like that?
Well, imagine you're an engineer designing a bridge.
Oh, okay.
You need to understand all the forces acting on it, right?
Gravity is pulling down, wind might be pushing sideways,
Mm-hmm.
and the weight of cars is pushing down on specific points.
Right.
Vector components let you analyze those forces
Okay.
in a much more precise way.
So instead of just knowing there's a force pushing on the bridge at an angle,
Yeah.
we can actually see how much of that force is pushing downward
Yeah.
and how much is pushing sideways.
Precisely. And that's crucial for making sure the bridge can withstand those forces and stay stable.
That's a great example. So vector components help us break down a complex force into more manageable pieces.
Right.
Almost like a recipe. We can see how much of each ingredient is
Yeah.
contributing to the overall force.
Exactly. It gives you a much deeper understanding of what's really going on.
Right.
And it's not just about forces. This applies to any vector quantity.
Okay, I'm starting to see how powerful this concept is. But this resource isn't just a static explanation,
Wait.
is it? It's interactive, right?
You're right. One of the things I love about this resource is that it lets you play around with different vector lengths and angles.
Cool.
You can see how tweaking those things changes the size of the horizontal and vertical components.
Okay.
And there's a fun activities section where you can even plug in specific values.
Okay.
Let's say 500 meters at 63 degrees.
Mhm.
And the resource will calculate the components for you.
So you can get a hands-on feel for how these components actually work. That's pretty cool. But does it get into the math behind those calculations?
It does touch on it. It mentions a couple of equations.
Yeah.
Akos theta,
Yeah.
and ios and theta.
I remember those from physics class. They look a little intimidating.
Yeah.
But I'm guessing they're not as scary as they seem.
Not at all. And we don't need to get bogged down in the nitty-gritty math right now.
Right.
The important thing is to understand that there are formulas that allow us to calculate those components precisely.
So it's like having a toolbox with all the right tools for the job. We might not need to use every tool every time, but it's good to know they're there when we need them.
Exactly.
But before we get too far ahead, I want to make sure I'm clear on the basic concept here.
Mm-hmm.
We've got this vector pointing at an angle, let's say 30 degrees above the horizontal.
Okay.
What are those components actually telling us? Are they like the shadow of the vector if we shone a light on it from different directions?
That's a really insightful way to put it. It's almost like you're shining a light from directly above
Yeah.
to see the horizontal component.
Yeah.
And a light from the side to see the vertical component.
Okay, I like that. So they're not literal shadows.
Right.
But they represent how much of that vector is acting in each of those directions.
Exactly.
And by understanding those components, we can analyze how that vector is influencing things in the real world,
Yeah.
whether it's a force on a bridge or the trajectory of a projectile.
Exactly. And that's what makes vector components such a powerful tool. They give us a way to break down complex movements and forces into smaller, more manageable pieces,
Right.
making them much easier to understand and work with.
This is already making so much more sense. But I have to admit, when I first heard the term vector component,
Yeah.
it sounded a bit abstract and intimidating.
Right.
Now it feels like I'm starting to see the practical side of it.
Right.
But what about for someone who's not an engineer or a physicist?
Right.
Why should they care about vector components? How does this apply to their everyday lives?
That's a great question. You know, it's interesting how something like vector components can seem so abstract at first,
Right.
but then you start to see them everywhere
Right.
once you understand the concept.
You're absolutely right. Like, I'm already starting to think about how those forces are working on the car
Yeah.
when I'm driving.
Right.
But I'm guessing there are even more examples out there.
Oh, yeah, definitely. There are tons of examples. Think about navigation. Ships and airplanes
Yeah.
use vectors and their components
Oh, okay.
to chart courses,
Mm-hmm.
taking into account wind and currents.
So if a plane is flying northeast, but there's a strong wind blowing from the south,
Yeah,
the wind is kind of pushing the plane off course.
exactly. By understanding the components of both the plane's velocity and the wind's velocity,
Okay.
navigators can calculate the necessary adjustments to stay on track.
So those pilots aren't just eyeballing it, they're using vector components
Right.
to make sure they get to their destination.
Right.
That's pretty cool. And it makes me think about how we use GPS on our phones.
Yeah.
Is that using vectors too?
It absolutely is. GPS relies on a network of satellites
Okay.
to pinpoint your location.
Right.
And each satellite signal can be represented as a vector.
Okay.
By analyzing the components of those signals,
Mm-hmm.
your phone can figure out exactly where you are on Earth.
Wow. So vector components are working behind the scenes of our everyday lives even when we don't realize it. That's mind-blowing. But I have to admit, I'm still picturing vectors as arrows on a piece of paper. Is there a way to think about them more visually in the real world?
There is. Imagine you're watching a sailboat race. The boats are all moving at different speeds and in different directions.
Right. And the wind is probably a factor too, pushing them in different ways.
Exactly. Each boat's movement can be represented as a velocity vector,
Okay.
showing both its speed and direction.
Right.
And the wind's influence can also be represented as a vector.
Okay, so we've got all these vectors pointing different directions. How do the components come into play?
Well, let's say one of the boats is trying to sail directly north, but the wind's blowing from the east.
Okay.
The wind's vector will have a horizontal component pushing the boat westward.
So even though the boat is pointing north, the wind is kind of pushing it sideways.
Exactly. To counter that, the sailor needs to adjust the sail and create a force vector with a westward component that cancels out the wind's effect.
So it's like a tug of war between the wind and the sailor is using vector components to make sure the boat stays on course.
That's a great analogy. And the sailor can use their knowledge of vector components
Right.
to figure out exactly how much force to apply in which direction to counteract the wind and reach their destination.
This is really fascinating. It's like a whole new way of seeing the world. Are there any other examples where vector components play a key role?
Oh, there are countless examples.
Right.
Think about sports. A basketball player throwing a ball towards the hoop
Yeah.
needs to consider the ball's velocity vector, factoring in both the speed and angle of the throw.
And the components would help them figure out how much force to put into the throw
Exactly.
to make the basket.
Or consider a golfer aiming for the green.
Okay.
They need to factor in the wind's effect on the ball's trajectory, which can be analyzed using, you guessed it, vector components.
So basically, anyone who needs to precisely control the movement of something is probably using vector components whether they realize it or not.
Right.
And I'm guessing this applies to things beyond just physical movement.
You're right. Let's take something seemingly unrelated. Computer graphics.
Computer graphics. How do vectors fit into that?
In computer games and animations, the movement of characters and objects is often controlled using vectors.
So when that character runs across the screen or that ball bounces off a wall, are those movements being determined by vectors?
They are.
Yeah.
The smooth, natural-looking movement, you can thank vector components for that.
Okay.
By manipulating the horizontal and vertical components of a character's velocity vector, animators can create really lifelike movement.
So if a character jumps and lands, the animators are carefully adjusting those components to make it look like gravity is acting on them?
Precisely.
Wow.
And that's just scratching the surface. Vector components are also used to create lighting effects.
Okay.
Simulate things like flowing water or smoke.
Yeah.
And even build 3D objects.
Wow. It's like vectors are this secret language that's driving so much of what we see and experience in the digital world. And to think, it all boils down to this concept of breaking a vector down into its horizontal and vertical parts. It's so simple, yet so powerful.
That's the beauty of it. And once you understand those fundamental concepts, you start to see them everywhere.
This is really blowing my mind. But I have to admit, we've been talking about a lot of real-world examples, and I'm starting to wonder, when we talk about vector components, are we always talking about horizontal and vertical directions? Or could those components be in any direction?
That's a fantastic question. And it shows you're really starting to think critically about this concept.
Oh.
Well, you're absolutely right. While horizontal and vertical components are the most common and often the most useful, we're not limited to just those directions.
So we could break a vector down into components that point north and east, or even at some other random angle?
We absolutely could. It all depends on what's most helpful for the problem we're trying to solve. Sometimes choosing different directions for our components can make the calculations easier or give us a better understanding of what's happening.
That makes sense. It's like we're choosing the best tool for the job.
Exactly.
Sometimes a hammer and a screwdriver are all we need, but other times we might need a more specialized tool to get the job done right.
That's a great analogy.
Yeah.
And it highlights the flexibility of vector components. We're not stuck with just one way of looking at things. We can choose the directions that make the most sense for the situation.
So to go back to our bridge example, if the wind was blowing at a weird angle, we could choose components that line up with the bridge's structure, even if those directions aren't perfectly horizontal and vertical.
Exactly. That would allow us to see how much of the wind's force is acting directly on the bridge's supports.
Okay.
Which is crucial for determining its stability.
This is so cool. It's like we've unlocked a whole new level of understanding. And I'm starting to realize that this isn't just about plugging numbers into formulas. It's about using this concept of vector components to analyze and solve problems in a creative way.
I couldn't have said it better myself. And that's what makes this topic so fascinating.
Right.
It's a bridge between abstract mathematics and the concrete world around us.
I'm so glad we dove into this. I feel like I'm seeing the world with a whole new set of eyes. But I have to admit, when we first started talking about vectors, I was a little worried about getting bogged down in the math.
I know what you mean.
Is there a way to get a better grasp on those formulas without feeling like I'm back in high school physics class?
Absolutely. And you know, it's interesting you mention that because one of the coolest things about this interactive resource is that it lets you explore the math behind vector components in a really hands-on way.
Oh, really? How so?
Well, remember those equations we talked about earlier? Acust theta and iacint theta.
Yeah, the ones that look a little intimidating?
Right. The resource actually lets you play around with those equations.
Oh, cool.
You can change the length of the vector, the angle, and see how it affects the values of the components.
Wow.
You can even graph those components.
Okay.
And see how they relate to the original vector.
So instead of just memorizing formulas, I can actually see how they work in action. That sounds way more fun than just staring at equations on a page. But I have a confession to make. I haven't actually touched trigonometry since high school.
Oh, really?
Would I need to brush up on sine, cosine, and all that before
Yeah.
I could really understand these equations?
That's a great question. And honestly, having a basic understanding of trigonometry will definitely help you delve deeper into the math behind vector components.
Okay.
But the good news is you don't need to be a trigonometry whiz to start experimenting with the resource.
So I could still play around with the interactive parts and get a feel for how the equations work, even if I don't fully grasp all the trigonometric details.
Exactly.
Yeah.
And as you experiment, you might find yourself getting curious about those trigonometric functions and wanting to learn more. It could even be a fun way to rediscover some of those concepts you learned back in high school.
I like the sound of that. It's like the resource is inviting me to go on a learning adventure. I can start with the basics and then delve deeper into the math as I feel more comfortable.
Right.
But I'm curious, besides the interactive parts of this resource, are there any other ways to get a more intuitive understanding of how those equations work? Like, can you give me an example that would make those formulas click in a more real-world way?
I can. Imagine you're standing at the base of a really tall building.
Okay.
And you want to figure out how far a window washer is from the ground.
Okay.
You know, the length of the ladder they're using, let's say it's 50 meters.
Okay.
And you can estimate the angle the ladder makes with the ground. Let's say it's about 60 degrees.
Okay, I'm picturing it. So we have a ladder leaning against the building, and we know the length of the ladder and the angle.
Right.
How do vector components help us find the height of the window washer?
Well, we can think of the ladder as a vector, with its length representing the magnitude and its angle representing the direction.
Okay.
And we can break that ladder vector down into two components. A horizontal component representing the distance along the ground to the base of the ladder.
Okay.
And a vertical component representing the height of the window washer.
Okay, so the ladder is like a vector pointing diagonally upwards, and we're splitting it into a horizontal part and a vertical part.
Exactly.
Yeah.
And to find that vertical component, the height of the window washer, we can use the equation I is in theta.
So in this case, A would be the length of the ladder, which is 50 meters.
Right.
And theta would be the angle, which is 60 degrees.
You got it. So if we plug those values into the equation, we get I 50 sin 60, which gives us approximately 43.3 meters. So we know the window washer is about 43.3 meters above the ground.
That's amazing. So we used that equation to find the vertical component of the ladder vector, which in this case represents the height of the window washer.
Exactly.
I'm starting to see how those formulas can be used to solve real-world problems, but what about the horizontal component? What does that represent in this scenario?
The horizontal component represents the distance from the base of the building to the point where the ladder touches the ground.
Okay.
And to find that, we can use the other equation, ACOS, equals theta.
So if we plug in the values, we get ACOS equals ACE, which gives us 25 meters.
Right.
So the base of the ladder is 25 meters away from the building. It's starting to feel like we're solving a geometry problem.
And that's the cool thing. Vector components connect math to the real world in a really tangible way. They give us a tool to understand and analyze things that we see every day.
This is making so much more sense now. And it's funny how we started with this resource designed for secondary students. And we've already gone so much deeper into the topic. I'm starting to see how much potential there is to keep learning and exploring this concept. But before we get too carried away, let's take a step back and think about the bigger picture. You mentioned that vector components are everywhere once you start looking for them. What are some of the most surprising or unexpected places where you've seen them at play?
You know, it's interesting how we often think about math as this abstract theoretical thing.
Yeah.
But when you start to see how it connects to the real world, like with these vector components, it suddenly becomes so much more interesting.
Absolutely. For me, it's seeing how these simple mathematical concepts can explain complex phenomena in nature.
Yeah.
Like the movement of planets, for example.
That's a great one. A planet's orbit.
Yeah. How does that work?
Well, a planet's orbit isn't a perfect circle. It's more of an ellipse. And the speed of the planet changes as it moves along that elliptical path.
So it speeds up when it's closer to the sun and slows down when it's farther away.
Exactly. And that change in speed and direction can be described using vectors.
Okay.
And by breaking those vectors down into components, we can analyze how gravity is influencing the planet's movement at every point in its orbit.
So even though the planets are moving through space in these complex elliptical paths, we can still use these simple tools, vectors and their components,
Mm.
to understand those movements.
That's the amazing thing.
Yeah.
And it's not just planets.
Right.
We can use vectors to model the movement of anything from a baseball flying through the air to a tiny particle moving inside an atom.
Wow. It's like we have this universal language that can describe movement at any scale.
I love that way of putting it. It's a universal language of motion.
Yeah.
And it all comes back to those fundamental concepts we've been discussing.
Right.
Magnitude, direction, and those all-important components.
This has been such an eye-opening deep dive.
Yeah.
I feel like I'm seeing vectors everywhere I look now. But I'm curious, are there any common misconceptions or pitfalls that people tend to fall into when they're first learning about vectors?
Oh, definitely.
Yeah.
One of the biggest ones is confusing vectors with scalar quantities.
Right.
Remember, scalars only have magnitude, no direction.
Right, like temperature or mass. You don't say it's 20 degrees Celsius to the north or I weigh 70 kilograms to the east.
Exactly. But sometimes people forget that crucial distinction and try to apply the same rules to both scalars and vectors, which can lead to some pretty confusing results.
So it's important to always keep that direction component in mind when you're working with vectors?
Absolutely.
Yeah.
And another common mistake is thinking that all quantities with magnitude and direction are vectors.
Oh.
We talked about this earlier with things like angular displacement and electric current.
Right. Those quantities have a size and a direction, but they don't follow the same rules of addition as true vectors.
Exactly. Vectors have their own special set of rules.
Yeah.
And it's important to understand those rules if you want to work with them correctly.
So it's more than just having magnitude and direction. There's a whole underlying structure to how vectors behave.
Precisely. And that's why it's so important to have good resources that explain these concepts clearly, like the one we've been discussing.
That resource has been so helpful throughout this deep dive. I love how it introduces these complex ideas in a way that's easy to understand, and especially how it makes it interactive so you can actually play around with the concepts.
I agree. I think that hands-on aspect is crucial for really grasping the power of vector components.
It's one thing to read about it in a textbook, but it's another thing entirely to see those components changing in real time as you adjust the length or angle of the vector.
Exactly. It makes the learning process so much more engaging and intuitive.
This deep dive has been a fantastic reminder of how fun and rewarding it can be to explore new concepts. And I have a feeling our listeners are feeling inspired to learn even more about vectors now.
I hope so. And for anyone who wants to delve deeper, there's a whole world of fascinating resources out there, from textbooks to online courses, even interactive simulations.
That's great advice. And don't be afraid to experiment and find those learning methods that work best for you. Whether it's building models, drawing diagrams, or playing around with those interactive tools, the key is to make the learning process your own.
I couldn't have said it better myself. And remember, the most important thing is to stay curious. Keep asking questions, exploring new ideas, and who knows what you might discover.
Well said. It's been an absolute pleasure exploring the world of vectors with you today.
The pleasure was all mine. And to all our listeners out there, happy vectoring.